The graph of f prime is below. Use it to determine where the inflection points are and where f is concave up and concave down. If there are multiple inflection points, separate them with a comma. Okay, so be very careful in this problem because the graph given is not of a function, but a function's derivative, which means we can't just look for things that look like inflection points and call them the inflection points. We have to think about what it means to be an inflection point. Like, for instance, if we start brainstorming how derivatives and functions relate. One thing that we know is that if a function is increasing, then that tells me that its first derivative is greater than 0. If a function is decreasing, then that tells me that its first derivative is less than 0. If a function has a critical number, which I'm going to call a min or max at this point because we have a smooth continuous curve, so there's no discontinuities. I'm just going to say a min or a max. That happens when the first derivative is equal to 0. Okay, now here's where we have to take a bit of a leap. So the only reason we know that this graph is a derivative is because we said it was. And that kind of locks in some properties as to how we interpret whether it's positive or negative, increasing or decreasing, or has zeros. But other than we said that it was a derivative, it doesn't really have to hold to that. This could have been an original function, it could have been a derivative, it could have been a second derivative. The properties from one function to its derivative hold from the original function to the first derivative as if they were relating the first derivative to the second derivative. Here's what I'm saying. So, if the first derivative has a minimum or a maximum, then what that's going to mean is that the second derivative has a 0. Okay, because the relationship is between one derivative. Okay, so if a second derivative is equal to 0, that tells me I have an inflection point. So what I'm looking for here are values where the first derivative has a minimum or a maximum. So here and here, that's where I'm going to have inflection points. So at -2 and +1. Now, the intervals of concavity are pretty straightforward at this point, because if we assume that this relationship holds from a function to its derivative, then let's just look at the relationship between the first derivative and the second derivative here. So if the first derivative is increasing, then the second derivative is greater than 0. If the first derivative is decreasing, then the second derivative is less than 0. And we know the second derivative, when it's positive, tells us we're on an interval that is concave up. And when it's negative, we're on an interval that is concave down. All right, so the first derivative is increasing on this interval here. So that means we are concave up on the interval from -2 to +1. And then we are decreasing on the rest of the intervals. So from -infinity to -2, and then from 1 to +infinity. Because that's where the first derivative is decreasing, so that tells me where my second derivative is less than 0 or concave down.